In this video, we'll provide an overview of the photolithography process. In the previous video, we described the principles of photolithography. Photolithography, in essence, uses photons to transfer the patterns on a lithographic mask onto a photosensitive layer deposited onto a wafer. A photolithography process involves three main steps. The first step is coating the wafer with a layer of photosensitive resist. The photoresist are photosensitive polymers that will undergo a specific chemical reaction upon light exposure. To create the photoresist film, the wafer is first placed onto a vacuum chuck, and the photoresist is then dispensed onto the wafer. The chuck is then spun at a prescribed speed and time to achieve a target polymer thickness. The second step is exposure of the light. In the previous video, we explained different wafer printing methods, including contact printing, proximity printing, and projection printing. Upon exposure, the patterns of the mask are imaged onto the photoresist layer. Final step is to use an appropriate solvent to resolve the image of the mask pattern in the photoresist layer. Let us now delve into the typical chemical structure of photoresist. Photoresist typically consists of three main components: a resin polymer, which is the backbone of the photoresist, a photoactive compound, or PAC, which, as the name indicates, causes the change of the resist behavior upon light exposure, and a solvent, which keeps the resist in a viscous form. Let's consider the G-line photoresist and examine the design of the resist for the photolithography process. The resin polymer is not light sensitive and dissolves quickly in a developer at a rate of about 15 nanometers per second. On the other hand, the role of PAC, or photoactive compound, is to inhibit the dissolution of the resist material in a developer. The common PAC molecules in a G-line and I-line resist is diazoquinone. Specifically, diazoquinones are insoluble in typical developers, therefore reducing the overall dissolution rate of the photoresist to 1 to 2 nanometers per second. Upon exposure, however, diazoquinone molecule undergo a structural change. This structural chemical change results in the so-called Wolff rearrangement, where a carbon atom leaves the ring structure to stabilize the molecule. Finally, the resulting molecule transforms into carboxylic acid in the presence of the water moisture from the room air. The carboxylic acid is readily soluble in a basic developer such as TMAH, KOH, or NaOH. Note that the resin is also readily soluble in this solution. Therefore, the exposed regions of the resist dissolves fast at a rate of 100 to 200 nanometer per second. The unexposed regions of the resist are, however, unaffected by the developer, allowing the resist to reproduce the image of the mask. Unlike the G-line resist, the deep UV or DU resist are based on a completely different chemistry. The deep UV resist make use of a chemical amplification process using photoacid generators or PAC molecules. The illustration here shows an example resist based on the PHS polymer with attached blocking groups, which are insoluble in the developer. The incoming photon react with the PAG molecule, creating an acid molecule shown as a proton here. The acid molecule acts as a catalyst during the post-exposure bake and change the resist properties in the exposed region. Specifically, the insoluble blocked polymers is converted into an unblocked polymer that is soluble in an alkaline developer. Photoresists are commonly categorized based on their polarity as positive and negative photoresists. The illustration here shows how the positive resist and the negative resist behave upon exposure. Specifically, positive polarity refers to a type of resist where the exposed regions indicated with arrows become soluble in the photoresist developer. Therefore, after developing, the exposed regions dissolve and the unexposed regions of the resist produce the copy of the photomask image on the wafer. In the case of negative resist, however, the regions again indicated by the exposed regions indicated by arrows become insoluble in the photoresist. As a result, the unexposed regions dissolve after developing the resist, and the exposed regions produce a copy of the photomask image on the wafer. Let us now delve into the high-level details of the different steps in a photolithography process. The slide here shows the steps involved in coating a wafer with a photoresist. The first step is to remove the water molecules which are deposited from the room air onto the wafer surface. This step is performed to improve the adhesion of the photoresist to the wafer. This can be achieved simply by baking the wafer at sufficiently high temperature, for example 110 degrees Celsius, to evaporate these water molecules. The wafer is then briefly cooled down before coating it with the photoresist. The wafer coating with photoresist is done using a process called spin coating. This involves initially dispensing the resist onto the wafer and then spinning the wafer at a prescribed spin speed and time to obtain a desired photoresist thickness. Note that the photoresists are designed to produce a range of film thickness. As a result, the resist thickness is a design parameter which depends on the intended target and need of the fabrication process. For example, a thinner resist is helpful for improving the minimum feature size, while a thicker resist may be needed for performing a subsequent etching process. Here is an example plot showing how the resist thickness varies with the spin speed. As the spin speed increases from 750 to 3000, the film thickness decreases. According to this plot, the SU850 resist, the curve here, produces a 40 micron thick film at a spin speed of 3000 RPM and 100 micron thick photoresist at a spin speed of about 1000 RPM. After coating the wafer with the resist, a brief baking process is performed prior to the exposure. The reason for this baking step is to remove the residual solvent inside the photoresist. Manufacturers provide instructions in the product manual for performing this step. For example, the suggested time for performing the soft bake on a 40 micron thick SU850 at 95 degrees Celsius is about 5 minutes. The next step is to use an exposure system to transfer the image on the photomask onto the wafer. A photomask is typically made of quartz or lime glass. The glass mask is coated with an optically opaque material such as chrome or iron oxide. The design patterns are created permanently into the chrome film, shown as black rectangles here. The mask is placed in between the light source and the wafer, with the chrome side facing the wafer. Upon exposure, the light is blocked by the chrome patterns and passes through the clear regions of the masks and exposes the photoresist in these under the clear regions. The photoactive components in the exposed resist regions will prompt a chemical reaction as we described earlier in this video. An important requirement to successfully perform the exposure is that the photoresist can effectively absorb the UV photons. The plot here shows the absorbance of the photoresist with different thickness as a function of the wavelength. Based on the data here, the absorbance of this example photoresist decreases with increasing wavelength of the light source. Specifically, this example photoresist is virtually transparent to the H-line UV source. In contrast, it can effectively absorb the I-line UV source. The absorbance information guides the choice of the UV source for the photolithography process. The exposure time is another important factor for successfully transforming the mask image into the photoresist. Specifically, the number of photons that impinge onto the exposed region of the photoresist determines the quality of the image. Since there are a finite number of photoactive compounds within the exposed regions of the photoresist, the number of required photons for driving the desired chemical reactions must be adjusted. Overexposure due to elongated exposure times degrade the shape characteristics of the printed features. The micrograph here shows an example where the overexposure causes the broadening of the features on top portion of the SU8 resist. This brings us to the question of how to calculate the exposure time. The photoresist manufacturers provide the optimal energy density, which is known as exposure dose, in units of millijoule per centimeter square for performing the exposure process. On the other hand, the UV lamp source of an exposure system provides a specific power density in units of milliwatt per centimeter square. Therefore, the exposure time can be easily calculated with the knowledge of the UV lamp power density and the required energy density. Specifically, the exposure time can be calculated by dividing the exposure dose divided by the lamp power density. Assuming a lamp power density of 10 milliwatt per centimeter square and a dose of 60 millijoule per centimeter square, the exposure time can be calculated as 60 millijoule per centimeter square divided by 10 milliwatt per centimeter square, resulting in 6 seconds of exposure time. After exposure, portions of the photoresist are dissolved by chemical developer. Specifically, in the case of positive resist, the exposed regions are dissolved. In the case of negative resist, however, the unexposed regions are dissolved. For example, as we learned earlier, the exposed regions of a typical positive G-line resist produces carboxylic acids. Therefore, a basic solvent such as potassium hydroxide can be used for dissolving these acid-rich regions. In summary, we discussed the steps involved in the photolithography process. It simply consists of 3 main steps: the coating of the wafer with a photoresist, then exposure of the resist to the UV light through a lithographic mask, and finally performing a develop process in a solvent, which reveals the printed features in the photoresist.